We continue with Piotr Tourkine, who is going to discuss the Eikonal amplitudes on the celestial sphere. Go ahead.
Okay, thank you. And let me also start by thanking the organizers for putting together this very nice conference and inviting me to talk. So this is work in collaboration with Tim Adamo and Binu, who are in the audience, and Wei, who's already moved to the other side of the ocean, I guess. Or
Ben surnames and stuff.
Fuck, sorry. Okay, so let me switch immediately. This is a very embarrassing slide. Bin gave a talk in the conference, so you can find the correct spelling. Okay, so let's switch subjects. So the ultimate, I'm sort of an outsider in this field. So for me, the ultimate goal is really the S matrix, and of gravity in particular. And to some extent, the gold standard for gravitational scattering at high energies is this series of papers in the late 90s by Veneziano, Amati, Cefaloni, and Veneziano, whose name I did not misspell because it's a screenshot. And of course, Carlo and Rodolfo and many other people have since then taken up on these works and pushed them to. But let's consider this as sort of our gold standard. And the question that we will be investigating in this talk is, can celestial amplitude tell us something about Planck scattering in quantum gravity? And in that's not the last version.
That's what I don't know.
Ah, yeah, that's where the typo came from. Which one? Is this the second one, or
Yeah. That's the one.
is this one different?
You can.
Sorry.
No.
Jesus.
And there's a 50
I should have-
lines, of course.
Yeah, this is the same.
Yeah, I think you've clicked on the same flag for example.
So I
the
should-
rest would be.
First?
Yeah.
Yeah, okay. Okay, and let's not look at the first slide in
So,
too much details.
I can put it on.
Bin, I'm so sorry. Okay. So, exactly. So, in one sense, the results I'm going to present are a first step to understanding Planck scattering on the celestial sphere, and in another sense, we also propose a way to obtain well-defined and analytic gravitational celestial amplitudes. So, the reason, the motivation, the reason why. So Laura and everyone talked about the holographic motivations. My motivation is much more down to earth. Is that sometimes you need to go to other variables to render problems simpler and understand it better. For instance, the unitarity of the S matrix is much clearer if you trade the exchange momentum for angular momentum, and in that case, it becomes just that these objects are simply complex numbers of modulus smaller than 1. Likewise, the Eikonal exponentiation that was also alluded to by Pierre and a bunch of other people is much more clear in impact parameter space. So again, you trade the exchange momentum for some impact parameter variable, and the exponentiation is direct, it's immediate. And of course, these simplifications are not like coincidences or just chance. They occur because of symmetries of the problem and different kinematical regimes and so on. And so the hope is that celestial amplitudes that are, like I'll say in the next slide, and like Laura explained beautifully, in some sense, S matrix for definite boost states. So you change the exchange momentum and somehow the energy for boost and angle. And the hope is that it might tell us something non-trivial about these gravitational amplitudes. So, again, like Laura explained, these celestial amplitudes are obtained by changing definite energy states to definite boost states. So and the boost charge is this conformal weight, delta. So you end up with formulae where you take your bit of kinematics. So S is the center of mass energy, omega squared, omega is the energy, and T is the transfer momentum, and for 2-to-2 scattering, Z is some sort of is some function of the scattering angle. So you have these two variables s and t, and the way to get to this celestial amplitude we'll be looking at is to do this Mellin integral, where you fix z, so you fix the angle, and you integrate over all energies from 0 to infinity, and you do this Mellin transform with this kernel that has this number omega, which becomes the boost charge. So it's Mellin transform of these scattering amplitudes. That's what we will be looking at. And our concern here is, are these objects defined at all? And like Laura explained, sometimes they are not defined, and that most of the cases, when they are defined, they're badly non-analytic. Let's look, for instance, at the exchange, three-level exchange of a spin j between two scalars. So you have just two scalars, and they exchange a spin j particle. There is what? There is what? Chalk. Oh, yeah.
Yeah, if it's for one diagram, one shot is enough.
Okay, don't disturb me more. I'm ready. Okay, so you have this power of I mean, so they're a rational function, s to the j over t, and when you replace s and t by the suitable omega thing, you end up having to integrate some function which is just a power of omega between 0 and infinity. It's pretty bad. At best, it's a delta function if really you select beta to depend on j in such a way that and you have this factor of I. But this is very badly non-analytic, and yeah. And this is a slogan that Nima and collaborators like to put forward as celestial amplitude being anti-Wilsonian, because of course they mix being an integral over the entire range of energies. The trouble you have defining this integral comes from the fact that you have to go from 0 to infinity. If you stop in the middle, or if you start in the middle, life is simpler, but because you have to integrate over everything, you're dead. Okay, so let me just mention briefly some attempt also by these guys to make sense of these objects in some distributional matter. But for us, really, we will be trying to restore this analyticity. So the same thing happens if you don't just sum one term, but any finite number of terms. You have omega log omega. This is to some powers. This is some stuff you cannot integrate over the whole range of energies as well. They will diverge either at 0 or at infinity. But if you sum infinitely many terms, then your life becomes much possibly more interesting. For instance, if you sum infinitely many powers of this omega squared in this fashion, you get this not just finitely many powers of omega, which would render this thing badly ill-defined, but this exponential softens the UV and makes the whole integral convergent. And you get, in that case, a gamma function, which has very nice analytic properties in beta, has only poles in the negative real axis, and for the rest is analytic. And our working assumption, just like these guys, APRS, is that this analyticity is desirable, and we will be looking at ways to restore it. For them, actually, they got exactly this omega, e to the minus omega squared term from some entropic suppression. So they argued that if you scatter two particles at sufficiently small impact parameters, you will create a black hole, which is a standard argument. And this black hole is the amplitude for this for creating this black hole should be suppressed by the entropy of the black hole, essentially because you create there's a bunch of microstates, and the probability to exit in the same state as you entered must have something to do with the number of states in total. And the number of states is connected to the energy because the Schwarzschild radius is also connected to the energy, and you end up with this exponentially suppressed amplitude that has these nice analytic properties. Again, because the entropy, the black hole, the entropic suppression term made this integral converge, and you restore the analyticity in this way. So it has this poles, and I'll come back to the rest of the analyticity properties. In this paper, in our paper, so that's a toy model, okay? There's no first principle calculation on gravity that gives you this thing. It's a toy model based on some arguments which are solid, but in our paper, what we realized is that in gravity, what you're really doing is when you're not just exchanging one graviton, especially when you integrate over all energies, you're exchanging infinitely many gravitons, and that's in particular in some regime of energies correspond to this Eikonal scattering, which instead of producing this suppression factor, produces a phase which will act in the same manner and make everything well-defined, analytic in beta. So I get the pitch, so I cannot mess that up anymore. Let's see. So the Eikonal. Let me start with the Eikonal resummation. The first subtle point is that usually when you think of Eikonal, you would think it's valid in a regime of zero scattering angle. But what ACV figured is that because the I am destroying material. Because of the gravitational interaction is so soft, you can actually extend the Eikonal regime to some small but finite scattering angle. So it does make sense to fix the scattering angle and to integrate over all energies. I have no time to review Transplanckian scattering, but you can ask Carlo, or you can look at Sasha's lectures at the Bootstrap conference in Madrid this summer. Another aspect that I won't have time to cover really in this presentation is that the Eikonal scattering captures exactly, not in an approximate manner, but exactly the motion in some linearized backgrounds. Of course, that goes back all the way to Toft, who proved that you can scatter through a shock wave or scatter Eikonally, you get the same results. And in some series of paper with Tim and Andrea, we extended this to other to all linearized backgrounds. 5 minutes. Okay, so that's the Eikonal amplitude in gravity. It's made of the first term, three-level term that I told you about. Then you get this term, which is a phase, which you can recognize to be a phase. It depends on S and T. And what we want to do is to take this Mellin transform of this object. That's the guy we were looking at. We're looking at this Mellin transform of this infinite sum of diagrams. Let's see what we can do with that. Okay, so firstly, Newton's constant, there's no mass scale in this problem, so Newton's constant has to come with the energy, and since you are integrating over all the energies, it needs to factor out in front, so you get this g to the beta that goes out of the integral. You do a small change of variable, omega squared goes to omega, and you get this slightly simple looking integral. That's of this form, this omega to the beta, and then a phase. And what happens is that the phase helps the integral to converge. And to check this, you need to look at this integral close to zero, because of course, if beta is too negative, you have a pole, you cannot integrate. And so that's close to zero, and close to infinity, you need to check that the phase helps you enough. Let me cut entirely the part close to zero. Just say that you generate, if you do a careful analysis, you see that just like for the gamma function, you will generate poles at negative values of beta, and poles of higher and higher order. You see this omega log omega term that connects to the previous talk as well. And they're infrared effects, and like Carlo commented to us, they are completely non-universal, so they will receive corrections. Interestingly, just if you take the Toft amplitude, you get only single-valued zeta function, which is something that's been observed. We don't really know what's the significance of this. At infinity, that's the universal part, and that's what really makes the whole thing converge. So it's basically a straightforward calculation. You're wondering, how does this integral converge? So, of course, the interesting part happens for large omega, so you can Stirling expand these gamma functions. You get this guy here, which looks very much like the actual gamma function, except you have this omega to the omega. And it's an elementary calculation to show that this integral converges. You can do all the usual analytical continuation things with it. So that we kind of call it Eikonal gamma function because it's like the gamma function, and you add this extra omega to the omega term. So the summary so far, 2 minutes, thank you, is that again, the calculations are elementary. You can look them up in the paper. The Eikonal phase regularizes the Mellin integral. And since the true full gravitational amplitude does contain this infinite exchange of gravitons, our proposal is that this shows that this celestial gravitational amplitude actually exists, because this is really an entire part of the gravitational amplitude. The properties are that they are analytic in beta, apart from poles corresponding to IR physics. Now let's compare a bit more to the argument with black hole entropic suppression, and let's look at large beta. So you can do a saddle, which gives you a sort of semi-classical energy. Again, some things we discussed with Carlo. It gives you a semi-classical energy, which corresponds in turn to a semi-classical boost, which we have no, we don't know what it represents. It should represent somehow the scaling dimension of the exchange operator or the entire trajectory, I don't know. This would be very interesting to understand better. Overall, you get this kind of this suppression for the modulus square of the amplitude. Sorry, it's not a suppression; it's an enhancement. It's large. Beta is growing large. And let's compare it to the black hole ansatz. The black hole ansatz was essentially a gamma function, and we get something that's smaller by this 1/log beta correction to the beta correction. In both cases, this was exponentially suppressed in energy, and this was oscillating. Both of these things correspond to exponentially large in boost. It would be very interesting to, this gives a handle to try to understand the spectrum of the operators. Did you just zero? No, okay. In the CCFT. I don't have time to. One good thing would be to be able to compute this Mellin transform entirely. We cannot do it yet. We can do some dispersion relation argument, but we get a function that we can compute explicitly, which connects two functions which are not connected to each other. So we need one more relation, and we don't know where it could come from, but it would be nice if we could compute this integral explicitly, more than just computing the residues at the poles and the large beta and so on. And there's this thing that I didn't talk about at all, which is that this infinite sum of diagram can be seen as the movement in some, okay, I'll conclude, in some shockwave background, and we were also able to compute these Mellin transforms. There's something subtle in how you define the Mellin transform of the background, and which we clarified, and we defined a map to connect both results, and we also have this correspondence between Eikonal and motion in shockwave spaces to all others in a sense. And it's important because, of course, in ADS, these shockwaves play an important role as line operators. I didn't mention these papers, which looked at the Eikonal, but for completely somehow oblique different reasons, and they dropped the non-trivial terms of their phase, which interested us. Right, since I'm over time, I'll just leave it here. Thank you for your attention.
Questions?
Yes. So you Mellin the iconalized thing. Is there some order limit issue that you?
Let's see. There could
appear.
As long so yeah. I think the answer should be okay. Of course, one should be cautious, but since you by ACD you're sort of reassured on the fact that the Eikonal amplitude does extend beyond the strict Regge limit to some sort of finite angle, it will receive some kind of suppression factors coming from the emission of radiation, but they will not change the large Eikonal phase. And to some extent, so okay, we neglected this. In what I explained, I didn't talk about the emission of radiation. These guys produce an extra suppression, so they don't change the analytic properties. It will still be nicely analytic. But it's not an issue that you're looking at. It would have been a problem if you should have been restricted to fixed t, because you can go to S over t fixed. You can do the omega integral without doing something too crazy. Do you see what I mean? The two regimes. One would have been S going to infinity t fixed. If you were restricted to this, when you do the d omega integral with s equals omega squared and t equals minus z omega squared, you're in trouble because it means you really force z to go to 0 and so on. Here, if you keep z small, strictly speaking, you're doing something that makes sense. Apart from the fact that I didn't mention radiation, but yeah.
And sorry, I missed the definition of beta. So beta was, I guess, is it?
Beta is some combination of the conformal weights of each.
Yeah. So you don't assume it's complex in general, or are you looking on the principal series? Or
That's the point is that the resulting amplitude is analytic for beta anywhere in the complex plane apart from those negative values.
Thanks.
We have time for one quick one.
Hi, just two quick clarifications. So one is, I was under the impression that the Raclariu paper considered the Kabat and Ortiz kind of setup, and then they based it on that. So what was missed there?
It's not like they missed it. They looked at something different. They looked at the correspondence between the shockwave scattering and the Eikonal scattering, but then they got rid of the phase, which is the whole meat here. You need the phase to render this integral convergence. They didn't care about the analytic property of the resulting integrals.
Oh, I see. And just a quick follow on, in the papers by Carlo and others, there's like this imaginary contribution to the Eikonal phase, which comes out from like these loop contributions. So where does that enter in your analysis, if at all?
It would enter if it did not in what I explained. It does enter in the fact that you get some correction, you get some extra suppression to your Eikonal phase, which becomes then not a phase anymore, and this makes all the integrals even more convergent.
But like it's not in the celestial amplitude where you can analyze this properly in the IR part.
You can analyze safely the beta part, the large beta part, because it's the universal part. And then you modify your saddle, but just not even. I mean, it's very it's subleading corrections to the saddle. That's the leading order is really the one I showed. Thanks.